Hello everyone and welcome back. Today we're going to start with section 1.4. We're going to talk about linear dependence and independence. First subsection, we'll talk about the definition of these concepts. So we'll talk about the definition of linear dependence and independence for, of course, a general vector space. Our goal for this section is to generalize the concept of linear dependence and linear independence to general vector spaces. We've already seen them in linear 1 for Rn. I'm not going to use exactly the same definition, but we will prove that they're equivalent. All right, so here's the definition I will use. Definition 1.4.1. Let S be a subset of a vector space V. Then S is linearly dependent if there is an element V in S that can be expressed as a linear combination of the other vectors of S. So really I'm thinking of this element V is redundant. I don't need it to generate span of S. So V will be equal to A1 V1, A2 V2 plus AN VN, where A1, AN are in R, and then V1, Vn are going to be elements of S, but I'm not allowed to use V, so let me say minus V, so I'm removing the element V from S. Okay, so I can write one element of S as a linear combination of the rest of S. S is linearly independent, well, if the opposite, so if no vectors of S can be written as a linear combination of the other vectors of S. This definition works as is for infinite set, which is why I like it, but we will prove for finite sets that it's equivalent to what we used in a linear one. All right, so let's try an example. I have three vectors. I have 1, 2, 8, 2, 1, 1, and minus 1, 5, 27. I'm going to show that it's linearly independent using the definition. All right, so I need to check to try to write one element of S. So let's try I'm going to take the third just because that's what we're we're used to. Minus 1, 5, 27 as a linear combination of the other two. So of 1, 2, 8 and 2, 1, 1. All right, so if you remember how to do this, we put them in a matrix. We put our two building blocks as the first two columns, and then we put our target as the third. So 1, 2, 8, 2, 1, 1, minus 1, 5, 27. All right, I want to reduce this. If there is a solution, then I can write the third vector as a linear combination of the other two. All right, so let me reduce it for us so we don't waste time doing things we already know we can do. All right, so I'm getting this with 11 thirds minus 7 thirds and 0. All right, so since this is consistent, that means I can do it. So it is a linear combination. So let me write it. Minus 1, 5, 27 is equal to 11 thirds times the first vector plus minus 7 thirds times the second one. All right, so that means that when I look at the span of S, this vector is useless. I don't need it, so S is linearly dependent. All right, we'll do another example. We'll do part B in the next video.